We say GD&T, geometric dimensioning and tolerancing. But the standard that I always refer to, ASME's Y14.5, is actually just called dimensioning and tolerancing. Yeah, you think about it. What else would you dimension besides geometry? Geometry is so baked into this thing that it apparently doesn't even need to be in the title. We're left with dimensioning and tolerancing, a duality that's at the center of what we're trying to accomplish here. Here it is on a drawing of a steel tube, which I have as cut to length and deburred. This is drawing GD&T 00520. Here for the length, we have a dimension and a tolerance. What we're communicating with this is that the part is nominally 6 inches long, but we will accept anything from 5.88 to 6.12. But this is pretty much the ground floor when it comes to GD&T, and we're going up, way up, okay? Another great capability of the GD&T system is the ability to control geometry in multiple dimensions. Let's start with 2 dimensions. On this drawing, GD&T 00521, you'll see a rectangular panel made of thin sheet metal. I have these outside dimensions, 300 and 180 millimeters. The dimensions are inside boxes, so we call them basic dimensions. And then here I have a profile tolerance with a little circle on the crook of the arrow line. The circle tells us this is an all-around profile tolerance. The basic dimensions tell a story about a perfect geometry that I'm imagining as a designer. And then the profile tolerance is the amount of deviation from perfect that I can accept. These callouts establish an imaginary tolerance zone offset from the edges of this basic geometry. And in this case, the offset is evenly distributed. So the boundary of the tolerance zone lies 0.5 millimeters inside the basic geometry and 0.5 millimeters outside of the basic geometry. And then the edges of any manufactured part would have to be fully within that tolerance zone all around. If we simply said 300 plus or minus 0.5 and 180 plus or minus 0.5, then we would have to accept that a manufactured part could be made at the outer limit of that tolerance and that it could be tipped parallelogram style, I guess within the limits of the plus or minus 2 degrees on our drawing's tolerance block. By my math, if we took what we might call a horizontal measurement along the long edges of the part from corner to corner, we would get quite a bit more than 300. I get 307. So a simple profile tolerance like this can control form and orientation of geometry in 2-dimensional space, which is pretty powerful and important to my need as a designer. And by no means is it limited to simple rectangles. This is GD&T 00522. We might be able to use just a few words and symbols, backed up in this case by the CAD model, as you can see in General Note 3 here, to communicate a great deal about the requirements of a complex geometry. I would say CAD is a great tool for creating basic geometry, and synonyms for basic could be nominal, ideal, or perfect. It's interesting to think about that basic geometry being the dimensions on this drawing using Note 3 here. We could fully dimension this drawing view the way I had it in that sketch, but that's falling out of fashion these days. This is pretty efficient. Maybe this part will be made on a water jet machine with a toolpath programmed off the CAD geometry. Probably the inspector can likewise use that same CAD geometry to program their CMM or comparator. There's another whole ASME standard, Y14.41, devoted to model-based definition, where you never make a 2D drawing. You note all the geometric requirements in the CAD model. Sounds great, but I have still not worked with or for any organization that does MBD, at least consistently. For 20 years, I've been told that one day there will be no 2D drawings. But here I am, still making 2D drawings, still teaching young people how to make 2D drawings. I am certain that one reason the 2D drawing has endured is that almost anybody can open a PDF file or be handed a piece of paper. This makes the drawing broadly accessible to other professionals besides the engineers who don't have access to special, expensive software. Now, one thing that has changed is that the drawings are much less likely to be printed out and much more likely to be stored and shared electronically. Another thing that keeps the 2D drawing alive, I'm sure of it, is its ability to organize information and to communicate intent. On my drawings and many others, you'll see there's quite a bit of formatting, especially around the perimeter of the drawing, and this is meant to keep it in line with the drawing standard ASME Y14.100. But when it comes to these drawing views, we still have plenty of rules, but maybe also a little bit more artistic discretion, all in the service of communicating intent to our audience. And so here we take the idealism of the CAD model and its basic geometry and push it to new heights, especially with these orthographic views where we're looking straight down on the geometry. And then I can roll it over exactly 90 degrees in exactly the right way, so we're looking perfectly at the side of the part. This is not the way we generally experience the world, is it? But what it does allow me to do is to apply these dimensions to the edges. Oh yeah, the edges. How often in the real world do you see objects with super crisp, dark edges? In these drawing views, the edges dominate the visual depiction of the geometry. Not very realistic, but super helpful to our purposes. We know that any part that is delivered to us is not going to be geometrically perfect like this is. It won't be perfectly flat, and the special profile also won't be perfect. It could go in or out. There could be irregularities on the surfaces. There might be some taper. But as long as all of that is within these tolerances, then we say the part qualifies, okay? It is a GD&T 00522. But the starting point for communicating this tolerance, for knowing whether this part is qualifying or not, is that imaginary, basic geometry. Is that interesting to you? It's interesting to me. The idea that in this job, you constantly have one of your feet in the universe of the theoretical, the perfect, the basic. And then your other foot is in the universe of the real, the flawed, the actual. I'm sure we drawing people are not the only ones who participate in this kind of dualism. It's obviously a big part of engineering, mathematics, statistics. Actually, I think it's just a very human way to interact with the world, to make progress in the development of thought, to move between theory and practice. And it's the kind of thing that people have been thinking about for a very long time, if you'll follow me here for a minute. Have you ever seen this painting, The School of Athens? This is a fresco in Vatican City completed by Raphael in 1511. This whole scene is highly fictionalized, but if it really happened, it would be around the mid-300s BC. Kind of hanging out are some of the big names in ancient Greek philosophy, mathematics, and science. Raphael could not have been more clear about what is the focal point of this piece, where we have these two fellas taking a walk in their robes. The older guy on the left is Plato. The younger guy on the right is Aristotle. It's a nice day, and they're keeping it light with a conversation about the fundamental nature of reality. Look at the hands. Plato is saying, "You want the truth? It's up there." And then Aristotle is saying, "No, man, the truth is right here in front of us." Plato, as you know, was a real believer in fundamental truths, which he called forms. And he had an extremely strong belief in the soundness of geometry and mathematics as the highest expression of this. Supposedly, over the entrance to his academy, he had written something like, "Let none but geometers enter here," by which he meant people who similarly embraced geometry as like a bedrock of purity in this crazy, crazy world. Like you couldn't even be a smart or ethical person unless you first got on board with this idea. Plato wrote a thing called the Allegory of the Cave that describes human existence in a pretty stark way. He said we live our lives at the bottom of a cave, chained to a wall so that we can't look behind us to the cave's entrance. Light enters the cave, on its way illuminating forms that are perhaps up in heaven. But the forms are also behind us, so we can't see them. All that we see are the shadows that they cast on the cave wall in front of us. The forms could be shapes like cubes, circles, triangles, or any kind of thing like justice or good. They're perfect up in heaven, but by the time they get projected as shadows onto our cave wall, they are a distorted mess. Plato might say that our intellectual and even moral growth is stunted by living in this state of squalor. And how can you make sense of any one of these shadows until you recognize that it only came about because of a form up there? So for the philosopher or the geometer, the task is to develop our understanding of the forms. I really wonder what Plato would have made of CAD. Maybe he would be in awe of it as giving us almost like a godlike ability to generate forms with tremendous clarity and efficiency. If we bought Plato a seat of CAD software, maybe he would just disappear into it and we'd never see him again. Enter Aristotle. He's a student of Plato, but he also pushes philosophy and science into a whole new era by making it much more useful and practical. I have a good time and think about maybe Aristotle coming into Plato's cubicle and saying, "Hey, great master, I know you're having a great time at CAD here, but pretty soon we're going to have to order some parts from the machine shop. So if you could just like wrap it up a bit." And then Plato might say back, "Yeah, it's just, I'm really worried because I've been designing this cube and it looks great here on my screen, but I know when we get the parts delivered to us, it's going to be all messed up. The sides will be different lengths, the faces won't be square, the edges won't be sharp. It's almost like the one thing we can be assured of is that whatever we get, it's not going to be a cube like here on my screen." Aristotle would say, "Okay, let's not panic. Let's just start a drawing. This will be GD&T Guy 00523. We'll place some views, some basic dimensions, and even an all-over profile tolerance. I've always wanted to use one of those. We'll make it a nice loose tolerance too, so it's easy to manufacture. And Master Plato, because I know you don't like to think about tolerance very much, I'll just explain that the all-over profile establishes a tolerance zone that's like the space between two nested cubes. And each element of the 6 surfaces must lie within that tolerance zone." And then Plato would say, "Oh man, this is nuts. Look how distorted this thing could be. This one seems to be closer to a sphere than a cube." To which Aristotle would say, "Okay, you're right. This is not very cube-like, is it? So how about we fix this up a little bit with a new drawing, GD&T Guy 00524. We'll keep that all over profile, but we'll do another few things too. We'll put a flatness on all the 6 surfaces. We'll control the radii on the edges a little bit better. And then up in the general notes, well, these are a little creative, but I think they might work. The sides must be mutually perpendicular 0.4 millimeters, and the 3 widths must not vary more than 2 millimeters. But of course, Plato, never satisfied, says, "Geez, I'm still not happy calling that a cube." But Aristotle might say, "Well, that would be cube-like enough for me. If a part that conformed to all these requirements were delivered, I would pay the invoice." And scene. I hope I didn't overcommit to that dialogue. I'm probably out of my lane. But anyway, do you see how in my silly telling, Aristotle pulls us out of the trap of Plato's system and allows us to get to the business of making parts and building hardware? Plato looks at the CAD model, and even if it's not something he can hold in his hands or use to build anything, it is still the real GD&T Guy 00523 or 524. More real, more correct, more meaningful than any part that could ever be manufactured. Aristotle holds a manufactured part in his hands, inspects it, and if it meets all the requirements that are on the drawing, then it is a GD&T Guy 00524. Aristotle will call it a cube without any hesitation or doubt. It contains within itself the properties of cubiness. Those properties do not exist in some distant place. But who decides when a part is so irregular that it can no longer be called a GD&T 00524? I do, as the designer, when I make these callouts and I choose these numbers. And hopefully I do that based on whatever is required for the part to fit and function where it's being used. Okay, so do we throw Plato overboard and declare ourselves all to be followers of Aristotle? Maybe not so fast. How can I even start this design without knowing conceptually what a cube is? And when I depict it on the drawing, am I really going to show it as anything other than its basic geometry? I just can't do that. There are just too many different types of variations for me to show. It would be really confusing. But there is only one perfect depiction, isn't there? How can I specify flatness or perpendicularity without having some idea conceptually of what that means? How can I do an inspection without fixturing or metrology equipment that is very accurate in flatness and perpendicularity? I showed you the tolerance zone for that all-around profile callout. What are these nested cubes? Are they real in the material sense? Of course not. But conceptually, they are something that we can at least understand, and the meaning is clear. So yeah, tolerance zones are a great example of imaginary, theoretical, perfect geometry that we have to incorporate into our thinking. Another one is actual mating envelope, and this is drawing GD&T 00528. This part is a copper rod, 6 millimeters in diameter, plus or minus 0.12. Well, if you remember our rule number 1, the envelope principle, then you'll know that this has an important meaning beyond just the size limits, which is that the MMC size, 6.12, is not just a size limit. It is also a boundary that controls the form of the cylindrical feature. So this rod can be bent or bulging, tapered, whatever you can imagine, as long as it happens within this boundary. And I'm pretty sure in this case that the boundary can also be called the feature's actual mating envelope. And for this one, it's pretty easy to think about a gauge that could be made to check this actual mating envelope. And then you could run down the part with a micrometer or calipers to check the LMC size limit. Of course, even the gauge itself could never be perfect, but you would want it to be of a high enough quality that it could be relied upon as a simulator. But that's all it could ever be, is a simulator. It's the same kind of thing when it comes to virtual condition too. This is drawing GD&T 00529. This might be the very most stripped back illustration of virtual condition, but it happens when you have a size limit and a geometric tolerance. And the geometric tolerance has to have a material condition modifier, like this circle M, MMC symbol. So this is a straightness tolerance, a tolerance of form, and in a way it cancels out rule number 1, but maybe more accurately, it takes over some of the duties of rule number 1. With this one, I'm going to add the MMC size, 6.12, and the tolerance, 0.38, and get a virtual condition of 6.5. That's nice. That virtual condition would be an imaginary boundary, a perfect cylinder, 6.5 in diameter. So that's rule number 1 and virtual condition. Super important concepts when it comes to one of the core missions of GD&T, which is to ensure fit between parts. And to access those concepts, you need to have some level of comfort with abstract, imaginary geometry. But nowhere is this more true than when it comes to the datums and the datum reference frames. I've said it before and I'll say it again. This is the hardest part about GD&T. And to a great extent, it is hard precisely because you're moving back and forth between the two universes of perfect forms and imperfect parts. You've probably heard before that datums are imaginary objects like points, lines, axes, and planes, in the words of the standard, theoretically exact, and that these can come together, for example, as three mutually perpendicular planes to create a coordinate system in XYZ space. Well, I've paid enough attention to popular physics over the years to know that this idea of Cartesian space is a real abstraction. What is a flat plane or a straight line, after all, in a universe where gravity can stretch and bend spacetime? But even if the datums and the datum reference frames are a real abstraction, they are one of our greatest tools for communicating geometric requirements. And they even become highly practical for inspection, especially when we have access to high-quality datum simulators. This is drawing GD&T 00525, a machined aluminum part that I'm simply calling ARM. There's a lot going on in this drawing, but I want to jump in and talk about the position of this undersized 3/4 inch hole, especially in relation to the mounting surface of the part, which I have called out as the Datum A feature. Just the way that this part is kind of cantilevered away from the mounting surface, it would be pretty hard to inspect the position of the hole with like a calipers or something like that. But actually, that would be the wrong way to approach this inspection anyway. And that's just because of the way that I have the mounting surface called out as the Datum A feature. And then I have this 1.860 dimension with the box around it, and then an 8 thousandths diameter position tolerance on the 3/4 inch hole, referencing Datum A as primary. This has one very clear interpretation, and it starts with the fact that there is this Datum A, a plane. And we can simulate Datum A with an inspection surface. For example, this chunk of precision ground granite slab. Next, we can imagine that there is this perfect line or axis floating up here exactly 1.860 away from Datum A and perfectly parallel to it. And then there could be a cylindrical tolerance zone, more imaginary geometry, exactly 8 thousandths in diameter and perfectly centered around that axis. There's still no part being inspected here, just this theoretical imaginary geometry. So when we do go to inspect the position of this hole, we are looking to see whether something called the derived median line of the actual hole lies fully within that tolerance zone. Importantly, note that with this method, we are taking the measurement from the datum simulator and not from the flat feature on the bottom of the part. Let's add another datum, okay? This is GD&T 00526. This one has the same Datum A feature, but it also now has this Datum B feature, which is along this little edge. And have a close look because I did something kind of clever because this surface goes up into a radius. In the detail view, I use this datum target and a chain line to limit the datum feature and keep it away from that radius. And also the chain line is dimensioned as 250. Okay, now on this one, the 3/4 inch hole is located to Datum A primary and Datum B secondary. This 820 dimension would be another tricky one to inspect with calipers. Good thing we don't need to. So we know that there is this Datum A plane and a perpendicular Datum B plane. And we can simulate those, again with our inspection surface and with a 250 gauge block. And we can locate the tolerance zone off the Datum A and Datum B simulators. Still no part. When it comes to the inspection, we would place the part on the Datum A simulator and slide it over into contact with the Datum B simulator. And then we check whether the derived median line is within the tolerance zone. I have just a few more points to make here, okay? We're saying that the Datum simulators are very high quality, very flat, and in the case of the Datum B simulator, very perpendicular to Datum A. Well, this drawing shows that the Datum A feature has 6 thousandths flatness, which is pretty flat, but of course still allows some variation. And then the Datum B feature has this 4 thousandths perpendicularity to Datum A. Pretty good again, but still not perfect. And you know, these datum feature selections are meant to very closely resemble the way that the part will be located in assembly. But the surface the arm bolts down to is going to have some flatness tolerance, and the feature it butts up against is going to have some perpendicularity tolerance. So why do we use the high-quality datum simulators? Shouldn't they be as flawed as the real parts will be? This reminds me of the line, all happy families are alike, and each unhappy family is unhappy in its own way. There are just too many ways that the features on the manufactured parts could deviate from perfect. We can't possibly simulate all of those. The best we can reasonably do is to put our parts into interaction with perfect or close to perfect geometry. Whoa, that's a big one. But we're moving on, okay? We gotta wrap up. What if you're still uncomfortable with these ideas? What if you don't want to be in the universe of forms? You say, I want to stay here in the real world, GD&T guy. I'm not doing the datums. I'm not doing the geometric tolerances. I'm doing like this GDTG 00527. I'm doing plus or minus tolerances that are simple and that everyone can understand. Well, okay. It's just not a very clear or precise way to express tolerance. Does 1.860 plus or minus 4 mean a measurement from the flat surface up to the axis of the hole? Could it be just from this edge up to the axis of the hole? Or how about from this edge over here? Let's hope not. Or maybe I just take my calipers and measure from the axis of the hole to some random place on that bottom surface until I get 1.860? Does this communicate everything we were saying on the earlier drawings I had of datum A? I don't think so. This doesn't really communicate at all what the origin of this dimension is, or what to do if there's any form deviation on this mounting surface. And you could go on through these callouts. This plus or minus 10 in the general notes is a total disaster. All of these plus or minus tolerances being used to locate features are actually quite ambiguous and poorly defined. And it's just because of the refusal to engage with the universe of forms. I hope you've enjoyed this. I've been thinking about making this video for a long time, and I'm glad to finally be putting it out in the world. If I can bring things back to our friends Plato and Aristotle, and whether we should be taking a side with one of them over the other, I think as far as GD&T goes, no. I think you can't get to Aristotle without the Platonic conceptualizations. It seems strange that things that we know do not exist, or at least are not tangible, could possibly be useful in producing real hardware. When I was first exposed to this stuff, it made me uncomfortable. Probably the same for a lot of you. But it is actually unavoidable, and it really should be embraced. And look, this is what makes us human beings, okay? Our ability to think abstractly. It is kind of a starting point for all of science and engineering. So don't be afraid. You can hold two ideas in your mind at the same time. Did you really get into engineering because you dislike challenging thoughts? Thank you so much for watching. I have a few more videos coming up that will use some of these ideas as a foundation. Until then, this is the GD&T Guy signing out.